Hello, today's topic is continuity and limits of trig functions. First, we're going to start about the definition of continuity at a point. You may have heard before that to be continuous, a function should be able to be drawn without lifting your pencil, so that it's all connected. That is an intuitive definition, but the official definition of continuity can't be learned until you have an understanding of calculus and limits. So here it is in the box. The function f is continuous at x equals c if and only if the limit as x approaches c of f of x is equal to f of c. So in words, a function is continuous at a point when the limit of the function at that point matches the output of the function at that point. So this definition, even though it looks like one little rule, actually requires three conditions for f to be continuous at x equals a. So those three conditions are, first, f of a is defined. You cannot have a continuous function if the function is not even defined at that given x value. Secondly, the limit as x approaches a of f of x exists. So not only do you have to have a defined function, you also have to have a limit at that x value. And lastly, the limit as x approaches a of f of x must equal f of a, which is like what we have here. And that kind of ties the function existing and the limit existing together. They have to be the same value. So, to the right in the box it says justify that the following is continuous at x equals 3 by using the three conditions of continuity. Okay, it's not saying is it continuous. They're telling us it is. They're just saying to justify it using the three conditions. So the first condition is that f of a, which our a value in this problem is 3, has to be defined. So what is it defined to be? Well, our domain of this piecewise function shows that when x is less than or equal to 3, we're on the top piece of the function. So that means we're going to use the upper piece of the piecewise function. So we'll do 3 squared plus 5. So 9 plus 5 is 14. So the function is defined at 3. Next, we're going to look at the limit. Does the limit exist? Well, in order for the limit to exist, the function needs to be approaching the same y value, 14, from both pieces of the graph. So we're going to substitute the 3 in to the lower piece. So 5 times 3 minus 1. And that does check out. It equals 14. So yes, the limit as x approaches 3 of f of x exists. And lastly, we need to see if the limit is equal to the function value. And since this was 14 on both pieces, the function and what it was approaching, this is a true statement. The limit as x approaches 3 of f of x is equal to f of 3, which is equal to 14. All three of those are tied together in step 3. Very important that you understand the three-part conditions for continuity. This sometimes comes up on an AP free response question. Justify that the function is continuous, and they may not even say using the three conditions of continuity. It is implied that you must do so, which is why I teach it this way. Okay. Moving along, discuss the continuity at points A, B, C, and D on this graph. So either the function's continuous or discontinuous, and we have to say how we know. So at A, what do you think? Is it continuous or discontinuous? Well, it looks like you have a point that has been removed and placed up above, which means you could not draw through that without lifting your pencil to catch that point above. So we're going to say it is discontinuous. But we're not just going to say that, we're going to say how we know. We want to check out these three conditions for continuity and see which one fails. Is f of a defined? Yes, there's a point. Does the limit as x approaches a of f of x exist? Yes, the function is approaching the same value from the left and the right. Is the limit that the function is approaching on f of x at the x value a equal to the point, the y-coordinate f of a? No, that's where it fails. So the third condition is where it fails. The limit as x approaches a of f of x does not equal f of a. All right, B. Oh, and when it says discuss in math, it doesn't necessarily mean like write a sentence. This is a discussion. You are showing which of the three conditions for continuity fails. So that's the reason why it's discontinuous. So a mathematical discussion can be done symbolically instead of in words, and often is. Okay, part B. Is this function continuous or discontinuous at B? Well, it looks like it's going up here to some positive number from the left. It looks like it's going down here to some negative number from the right. So those don't equal each other, so that is not a continuous function. So we're going to say discontinuous. And why? Is f of b, the x value b, defined? Yes, it is. It has a solid dot there. Does the limit as x is approaching b from both sides of the function exist? No. The left-hand limit and the right-hand limit are not the same, so the overall limit does not exist. So we're going to say the limit as x approaches b of f of x does not exist. Okay. C. Is this function continuous or discontinuous at C? Well, if I draw it, I'm going to have to lift my pencil to jump over that hole in the graph. So it is discontinuous. And which one of the conditions for continuity fails? Well, the function's not even defined there. There is no point at C. So f of C is undefined or not defined. All right. And you only need to list the first condition that it fails. We generally do look at this in a stepwise order. So it's going to fail all three, but you only need to list the first one. Okay, D. Oh wait, no, it doesn't fail all three. The limit does exist. I apologize. But we only need to list the first one it fails when we're justifying why it's not continuous. All right, so D. Is the function continuous at D? F of D is defined. There's a point. The limit exists. It approaches the same value on the left and the right side. And the function value is equal to the limit. So it is continuous. And for our discussion, we're going to list those three things. F of D is defined. The limit as x approaches d of f of x exists, and the limit as x approaches d of f of x is equal to f of d. So it meets all three requirements for continuity. Some students will ask me, can I just write the last one? As you can see, the last one doesn't explicitly spell out that f of d is defined. There could be some situation where somebody might want to say, well, neither one of them is defined, so those are equal quantities or something like that. So it really is important to list out all three conditions for continuity. This is on one of your note cards, and I want you to study those three conditions for continuity and use them when you're justifying continuity. Okay. Next, we're looking at not continuity at a point, but continuity on an open interval. The word open interval means that you have parentheses, not brackets, which means the endpoints of the interval are not included. So a function is continuous on an open interval AB if it is continuous at each point in the interval. A function that is continuous on the entire real number line from negative infinity to positive infinity is everywhere continuous. And here are a couple of different types of discontinuity. So we looked at some discontinuity up here. Now we're going to see if we can say what kind of discontinuity we're talking about. A removable discontinuity is one which can be fixed or repaired by relocating or adding one point. So a removable discontinuity would be like this first picture right here, because there's a hole in the graph, so all you'd have to do is plug the hole with 1 point and it would be continuous. Or similarly, when we looked at this graph up here at A, you don't actually have to add a point, you just need to relocate this point, slide it down into that hole, and then it would be continuous. So that is considered to be a removable discontinuity. Basically, a non-removable discontinuity is any other discontinuity, everything else. So when you've got a vertical asymptote that a function is replacing, you can't just fill in one hole there and then all of a sudden it's connected. That doesn't work. Or if you have a piecewise function where the pieces are not connected, you can't just plug in a point and all of a sudden that's going to meet. So those are considered non-removable discontinuities. All right, next we're going to discuss the continuity of each function. So on what intervals is this function continuous? So this first one is a parent function. Y equals 1 over x is the rational parent function, or sometimes called the inverse variation parent function. You will recall that its shape has a vertical asymptote on the y-axis, a horizontal asymptote on the x-axis. If I substitute a 1 in, 1 divided by 1 results in a 1, so it goes in the 0.11, and then it just kind of slides up toward the asymptote here and here. If I substitute in a -1 for x, 1 divided by -1 is -1, so -1 is a point on this graph, and then I can draw the function going towards those asymptotes here as well. So that's the general shape. Is this function continuous all along the entire x-axis for every real value of x? No, it's not continuous at 0 because there's a vertical asymptote there that I have to jump over. Everything less than 0 has continuity and everything greater than 0 has continuity, but at 0, that's left out. So we're going to write down that this function is continuous from -infinity to 0, leaving out the 0 with the parentheses, union, which means like and, the interval starting at 0 but not including 0 going to infinity. And we always use the open parentheses on the infinity and -infinity symbols because they are not a specific value that can be included. They're more of an abstract concept that the function just heads out towards. So it expands, it goes on endlessly without bound. So I'm going to ask that you use interval notation on these intervals. Oops. Okay, B. Here we have our g of x function equals x squared minus 1 over x minus 1. This is another rational function. I gave you a little reminder sheet of notes about rational functions on the first day of school, so if you need to refresh on any of the properties of rational functions, I would direct your attention to that reference sheet. But what you will notice in the numerator of this rational function is that it is a factorable difference of squares. And so it factors as x plus 1 times x minus 1. Square root of the first term, square root of the last term, 1 positive and 1 negative. Now, the denominator, x minus 1, has a common factor with the top and the bottom. So what that means is that there is a hole in the graph. the hole occurs at the x value that would cause the denominator to equal 0. So the hole in this graph is going to be when x is, whoops, I don't want to write x, I want to write the x coordinate, when x is 1, because 1 minus 1 would give me 0. Now how do we get the y coordinate of the hole in the graph? Well, if you were to cancel out that common factor, the rest of the graph is going to look like whatever's left behind, x plus 1. That's just a line with a y-intercept at 1 and a slope of 1, so rise 1, run 1. So just a linear equation, but we have a hole in it. So the y-coordinate of the hole is going to be whatever you get when you substitute this x-coordinate in for the x in the function after you have divided out that common factor. So basically we sub in 1 for x here. 1 plus 1 equals 2. Woohoo! First grade. Now, what does that mean? Well, it looks just like the line except for a hole in it. So it's going to be continuous from negative infinity until I reach the hole at 1, and then union 1 to positive infinity. So everywhere except for where the hole is at 1. All right. C, h of x is equal to the sine of x. Do you remember your parent function sine of x from pre-calculus? That function has a domain of all real numbers. It goes up as high as 1 and down as low as negative 1, and it just kind of goes back and forth and back and forth and back and forth. And you never have to pick up your pencil to draw the function. So this function is everywhere continuous, from negative infinity to positive infinity along the entire real number system. Or another way to write that is the set of all real numbers. And even if I tell you to use interval notation, you can use this because it represents a set of all real numbers. Same thing, these can be used interchangeably. Okay, moving along, creating continuity. What value should be assigned to f of 0 to make the function continuous at x equals 0 over here? Well, at x equals 0, there's a hole in the graph, and they've placed it up here at 0, 1. So if that whole point was to slide down to the origin, you'd have a continuous function there at the origin. So f of 0 would have to equal 0. Now, this second part here is somewhat more complicated. What value should be assigned to f of 1 to make the function continuous at x equals 1? When x equals 1, there's a solid point down here on the x-axis, and it slides on over here to x equals 2 and solid here. So this is like a constant function, a horizontal line here. Then up here, there's a hole at x equals 1, so it jumps down to a second piece of this piecewise function. That is considered to be a non-removable discontinuity. So this is kind of a trick question. What value should be assigned? There isn't one. So it's a non-removable discontinuity. I will tell you that the AP exam will never ask you a question like that. It would have a little piece on the end of it that said, if there is a value, or something to indicate that that might not happen. So they don't try to trick you. They will say what value should be assigned, if any, to make f of 1 be continuous. So just letting you know that that's not the way this question would be phrased on the AP exam. Next, we have a piecewise function. F of x is equal to x squared plus 5x plus 4, all divided by x plus 1. We're on this piece of the piecewise function when x does not equal negative 1, which means for every x value except for this particular one, negative 1. When x is equal to negative 1, we're on the other piece, which has a question mark, and we don't know what that piece is. So it says define f of negative 1 in a way that extends f of x to be continuous everywhere. So what they're saying is probably if we use this whole thing along the entire real number line, it would not be continuous. Let's investigate it a little further. This is a rational function. Is that numerator factorable? Let's see. So x times x gives me x squared. Factors of 4 that add up to 5 would be 4 times 1. 4 plus 1 is 5. And that would be plus for both factors. So notice the common factor, just like we had up above right here. So these factors divide out, leaving us with this linear function y equals x plus 4. So there's a hole in the graph, and the hole in the graph occurs when the x-coordinate is -1, because -1 is the factor that is the x value that would cause the denominator to equal 0 in that factor. And then if I were to substitute -1 in for the x here, -1 plus 4 would give me 3 for the output, so that's the y coordinate of the hole in the graph. So if I wanted to plug the hole, I would want the x value -1 to have the y value 3. So f of -1 would have to equal 3. Okay, moving on down. Find the constants a and b so that the function is continuous on the entire real number line. Number 1 I'm going to do with you, then I'm going to ask you to pause number 2 on your video and try it on your own to see if you can come up with it, and then you can turn the video back on to check. So f of x is equal to x cubed, so your cubic parent function, for all x values less than or equal to 2. So that's going to be your left side of the graph. Then f of x is equal to a times x squared. A is what we're trying to find here. What is the coefficient of x squared that's going to make this thing continuous? And we're on this one for all x values greater than 2. So from the x value 2 to the right, we're on this quadratic function that has a missing coefficient. So we want it all to be continuous. We want it all to be connected, okay? So I want the y value here to equal the y value here. So I want x cubed to equal ax squared. And where do they need to meet? Where do they need to be equal? When x is 2, because that's when I switch from this piece of the graph to this piece of the graph. So I'm going to substitute a 2 in for the x's and solve for a. So 2 cubed is 8, 2 squared is 4, so 4a, divide by 4 to get the a by itself. A is equal to 2. Okay, now before I leave you to try number 2 on your own, I'm going to help you just to think about it a little bit and get started. F of x is equal to 2, so that means like y equals 2, that's a horizontal line. For all x values less than or equal to -1. Then on this middle piece, f of x is equal to ax plus b. This is the one where you're trying to find a and b. You're trying to figure out what the a and the b are. Notice this looks a whole lot like mx plus b, which is the general form for a linear equation. So this is just some linear piece that we want to connect. And we're on it from -1 to 3. Then f of x is -2, so another horizontal line down lower for all x values greater than or equal to 3. So pause your video and see if you can figure out a and b. Okay, so coming back, hopefully you've gotten it all figured out. I'll go ahead and tell you so you can check and see if you were right. Did you discover that a had to be -1 and b had to be +1? If you did, woohoo! Good job, I'm so proud of you. If you didn't, it's okay. I'm going to walk you through it so you can see what might have helped to solve this problem. Now, I will start by saying there's more than one correct way to solve this problem. And if we were in class together, I would probably get some of you to share out how you got it if you got it correct. It's because I would imagine that within a classroom, different groups of students might have come up with different ways to solve this problem, and that's great and fine. So I'm going to show you one way. It's not the only way. It may not even be the best way, but I'm going to show you a way. Okay, so one way you could do it is kind of looking at it graphically. You could say at -1, I'm up here at 2, and that point's included, and it goes on this way. At x equals 3, 1, 2, 3, I'm down at -2, right here is included, and it goes on this way. So I need a line that connects these 2 points. What are the coordinates of those 2 points? Well, -1, 2 needs to go to 3, -2. If I have 2 points and I want to know the slope between them, I can use the slope formula. x1, y1, x2, y2, then sub it into m is equal to y2 minus y1 divided by x2 minus x1. So -2 minus 2 over 3 minus -1 is -4 divided by +4, which equals -1. So there's the slope. A has to equal -1. Now we need to know the y-intercept. So if we know the slope and we want to find the y-intercept, we can use this y equals, we now know a is -1, so -1 times x plus b. And we can substitute in either the first point or the second point for x and y and solve for b. I'll just sub in the first point. So the y value is 2 and the x value is -1. So 2 equals +1 plus b. Subtract the 1 on both sides, 1 equals b. Okay, I guess I could have put equal, let's see if I can even fit it, equals a here. So I have an 1 equals a, oh, -1 equals a, sorry, and 1 equals b. All right, and if you did it another way, that's awesome. And I wish I could hear about it with you, but we're not together, so I can't. All right. In the box, it says a function is continuous on the closed interval. So before we were talking about functions being continuous on an open interval where it had parentheses. Here we have functions being continuous on a closed interval with brackets. That means including the endpoints. If it is continuous on the open interval from a to b, as we discussed earlier, and the limit as x is approaching a from the right side of f of x is equal to f of a, and the limit as x approaches b from the left side of f of x is equal to f of b. So when you have a function listed in interval notation, they are always listed in order. A is always less than b. Okay, you always have to go from the smaller number to the greater number. It's not correct to reverse them. So this one is the littler number, this is the bigger number. So this is the one that's further to the left on the graph. So here we're saying as I come in from the right side of the graph, it needs to be going to whatever f of a is. And as I come in from the left side of the graph, it needs to be going to whatever f of b is, because this is the point that's on the right. So coming from the left-hand limit needs to land into that y value. So that basically means that the function travels toward whatever the y coordinate is at that end. So take a look at the examples at the bottom of the page. There are 4. Scoop the paper. So I'm going to put my x-axis numbers here. This is 1, 2, 3, 4, 5. So where is this function continuous? Well, starting at 1, going to 4, definitely continuous. Don't have to pick up my pencil. It's all connected. And now the question is, do we include the limits? Do we include the endpoints or not? If the function is sliding right up into the endpoint, then yes, we include it. So this should be a bracket 1, comma 4, close bracket here. So we're including them. How about on B? Should we include the 1 and the 4? This is the same graph except for they've left out that endpoint on the left. No, since the function is not defined at f of a, the limit coming in from the right side is not equal to the endpoint. So we're not going to include the 1. It's going to be an open parenthesis there. But we can still include the 4 because it is traveling toward that closed up dot. Now C looks a whole lot like B except for they've added this point up here. This is where we're getting at the fact that we're not talking about the domain of the function. The domain has matched the continuity for A and B. The domain is not going to match the continuity for C because the domain of graph C is the same as the domain of graph A from 1 to 4, including both endpoints, because it is defined on both endpoints. But because the limit coming from the right side does not equal that x value of 1, we can't include it when we're talking about where is the function continuous. So we're going to have the same as b, open parenthesis at 1, closed bracket at 4. Okay? Now for d, I suggest that you pause your video, give it a try, and then check to see if you're right. I'm going to assume that you have had time to do so since you paused your video, and go ahead and tell you what the answer is. So this graph is a piecewise function. The first one is kind of like A. It looks like it's connected at both endpoints right to where the graph was going. So I'm going to say hard closed bracket at 1, and that goes to 2, 3, and it's closed there also. Then we're going to have a union and say and this other piece. On this other piece, it's more like graph B. So we should have an open parenthesis at 3 because we don't want to include that point. It's not approaching a solid included point. And then that's going to go to 4 with a bracket here. And we're good to go. All right. Now we are going to talk about limits of trig functions. So it says it's number 1, consider the limit as x approaches 0 of the sine of x divided by x. So I'm going to get a graphing calculator out, and we're going to take a look at this. I'm going to press y equals, and alpha y equals number 1 to get my little fraction going on here. And I'm going to type this function in here, sine of x on top over x on the bottom. And I'm going to look at the graph. Okay, it's all kind of squished in toward the x-axis. It's hard to see very well, so I'm going to press zoom, and then I'm going to press 2 to zoom it in and enter. And now I'm much closer. Okay, it looks like the limit as x approaches 0 should be up here at 1. What do you think? Doesn't it look like it's going towards 1? This is the counting by ones along the y-axis. I can show you the window. X scale 1, Y scale 1. So that is 1. Now, if I go second graph and take a look at the table, at 0 there's an error. Okay, there is not a defined point when x is 0 because look, we'd be dividing by 0. That's not good. Division by 0 is not defined. So it's not actually 1 there. But the values are getting closer to 1 on each side, and we could count by a smaller number like 0.001 if we wanted to investigate it a little bit more tabularly like we did on the first day of school. But I will tell you it is 1. This is the limit. And this is one of your note cards. This is a trig limit that I want you to memorize. Now, I want you to also consider a relative of this limit. Let's go into y equals and clear this one out. Alpha y equal, no, just kidding, y equals alpha y equals number 1 to get my fraction back. What if I put the x on top and the sine of x on the bottom? So it's like the reciprocal of this function. Anybody want to make a guess what that limit would be? If you were with me, I'd say, tell me what you think. And I bet somebody would get it, but we're not together, so I'm just going to know that you all got it because you're all just my amazing students. And I'm going to hit graph so we can take a look and see what happens. Well, this graph looks very different from the last one, but it also looks like it's passing through the point 0, 1. And why might you predict that it would? Well, we did the reciprocal of this function, so you might consider that it could be the reciprocal of the limit. And what is the reciprocal of 1? 1 is 1 over 1. When you flip the top and the bottom with each other, it's still 1 divided by 1. So it is 1. So something neat about this one is that it actually doesn't matter whether it's the sine of x on top and the x on the bottom, or the x on top with the sine of x on the bottom. Both of those come out equal to 1. So I'm just going to write that down as a little reminder here. Okay, let's move on to number 2. Y equals, we're going to look at the limit as x approaches 0 of 1 minus the cosine of x divided by x. If you plug in the 0 for x, it's undefined, so kind of like the last one. No, y equals, and I'm going to press alpha y equals to get my fraction, 1 minus the cosine of x on the numerator and divided by x in the denominator. Graph. Okay, this one looks like it passes, whoa, let me move this over here, right through the origin. You see that? I'm going to put equals 0. It looks like it goes to 0. Is it 0? No. There's the same error message next to 0. It's not defined there, but it is approaching 0 on both sides. Okay? Now, what if we were to do the reciprocal of this one? Would it also equal 0? No. No, it would not. We could try it. X on top, 1 minus the cosine of x on the bottom, graph. It's totally undefined. There's a vertical asymptote there. So, ba-bum. All right. So, what about this one though? The limit as x approaches 0 of the cosine of x minus 1 over x. Wait a minute. That's a lot like this one, but they've reversed the cosine and the 1. So instead of being 1 minus cosine, it's cosine minus 1. I want you to consider that this would be equal to negative 1 times 1 minus the cosine of x over x, because the negative 1 would distribute, causing that 1 to be negative, and this negative 1 would also distribute to the cosine of x, making it be positive, so it'd be the cosine of x plus negative 1, or the cosine of x minus 1. That all means the same thing. And if you'll remember, we had a property of limits called the scalar multiple, where you could take a scalar multiple of a function, pull it out in front of the limit, evaluate the limit without it, which we already know is 0 because, you know, we just figured that out. And then we can say equals negative 1 times 0, which is 0. So this function actually has, okay, I had some technical difficulties. I apologize. So those are both equal 0. Number 4, the limit as x approaches 0 of the tangent of x divided by x. Well, wait a minute. These are the two limits we're memorizing, and neither of them had a tangent in it, so how are these possibly going to help us with this one? Well, those were all about sines and cosines. This is just tangent, but we can rewrite tangent with sines and cosines, can't we? Let's try it. The limit as x approaches 0 of the sine of x over the cosine of x, all divided by x. Remember that reciprocal function that gives you the tangent of x? Okay, so, or quotient rule is a quotient function. Okay, so this denominator I could make into a fraction by putting a 1 underneath it, and then I could rewrite it as the limit as x approaches 0 of the sine of x over the cosine of x, and then instead of divided by x over 1, I could do multiply by the reciprocal 1 over x. And you recall that you can multiply in any order. 2 times 3 is the same thing as 3 times 2. Whoops, I left it off my x here. So I'm going to switch my cosine of x and my x on the bottom. That's a legal move in algebra. So I'm going to say sine of x over x times 1 over the cosine of x. Now, this guy, this first one, is the one that we memorized. The limit as x approaches 0 of sine of x over x is 1. And then the other one I can actually do a direct substitution on, 1 over the cosine of 0, because the cosine of 0 is 1 from our unit circle. So 1 times 1 over 1, which is 1, equals 1. Beautiful. All right, number 5 is quite similar. We have a limit as x approaches 0 of the sine of x over the tangent of x. So I want to take that tangent and change it to sine of x over cosine of x immediately. So the limit as x approaches 0 of the sine of x divided by the tangent of x, which is sine of x over cosine of x. And so limit as x approaches 0 of sine of x over 1 times the reciprocal of the denominator, cosine of x over sine of x, means, boom, boom, those divide out to equal 1. And now I have the limit as x approaches 0 of the cosine of x. And that is a direct substitution problem. Cosine of 0 is equal to 1. All right, let's take a look at number 6. The limit as h approaches 0 of 1 minus the cosine of h quantity squared divided by h. So first thing I want to do is pull apart that numerator. Instead of having it be squared, I'm going to write out the interior of the parentheses twice. Cosine of h over h times 1 minus the cosine of h over 1. So this first limit is a memorized limit. It is 0. And the second one really wouldn't matter what it is, because if I multiply it by 0, it's going to be 0. But I could say it is 1 minus the cosine of 0 and do a direct substitution, which would be 1 minus 1, which is 0 times 0, which is 0. Is it absolutely necessary to show that right side? No, because 0 times anything is 0. All right. Okay. Number 7. We have the limit as x approaches 0 of the sine of 4x divided by x. Now, I want you to think about this limit, the sine of x over x. What is x here? X is any number, isn't it? X is a variable. It could represent 100, 1,000, a million, negative 100. It could be 2. It could be pi. It could be e. It could be a fraction like 2/3 or a decimal like 0.285. X could be any number. Any number that I substitute in here for x on the top and on the bottom. This would be, the limit would be equaling 1 as x is approaching 0. So when I go down here and say I've got the sine of 4x over x, it really doesn't matter that that's a 4x as long as the bottom also has 4x, because 4 times any number is still any number. So what would be really helpful here would be is if I have a 4 on the bottom, which I don't, but I could use some creative math technique to help me out here. I could say, what if I multiply this fraction times a clever form of that number 1, that being 4 over itself, because that just means I'm multiplying it by 1. But when I do that, I have the limit as x is approaching 0 of 4 times the sine of 4x divided by 4x. Oops, that's not an x. I'm all excited about this problem. And so this 4 has to come out in front because it's a scalar multiple of a function. So now I have 4 times the limit as x approaches 0 of the sine of 4x over 4x. And this, because this is just some x value that's equal to this x value, x is an unknown quantity, these are equal, this has to equal 1, just like our memorized trig limit at the top of the page. So we just go 4 times 1 is 4, and that's the answer. Now number 8 is very similar to number 7, except for it's kind of like a little bit extra. So let's see, what would really help for this sine of 6x would be if I had a 6x underneath it. And what would really help for this sine of 8x would be if I had an 8x up above it. So what if I look at the limit as x approaches 0 of the sine of 6x over the sine of 8x, but I'm going to multiply this thing, oops, I forgot my 8, times 6 over 6, so that'll get me my 6 on the bottom, and x over x, so that'll get me my x on the bottom also. But look, it also gave me the x that I needed on the top. So I'm going to multiply by 8 over 8 and have that 8 on the top. So I could rearrange this thing now. The limit as x approaches 0 of the sine of 6x over 6x. So I've used this, this, and this. And then times the limit as x approaches 0 of, let's put that sine of 8x on the bottom. So I use that. And then this 8x on the top. And what's left? 6 on the top and 8 on the bottom. And now I've used it all. Check, check. Okay, so this first limit is 1, and the second limit is 1. And the limit as x approaches 0 of a constant is just that constant, 6 over 8. And that is a fraction which simplifies to 3/4, which is the answer. Okay, it's our last example now, number 9. The limit as x approaches 0 of, in the numerator, sine of x times 1 minus the cosine of x, all divided by the quantity 2x squared. So, this kind of looks like both the two memorized trig limits put together, because it is. So we're going to go limit as x approaches 0 and take that sine x and put it over x, because I have x times x in the denominator with that x squared, so I can put one of those x's under the sine of x. And now I'm going to go limit as x approaches 0 of 1 minus the cosine of x over the other x underneath this one. X times x is x squared. What's left? Times the limit as x approaches 0 of 1/2. Whoa, I think I went off the side here. Fix this up. There we go. So this first limit is 1. The middle limit is 0. Those are the memorized ones we talked about at the beginning. And the limit as x approaches 0 of a constant 1/2 is just that constant 1/2. And when I multiply these three values together, that 0 causes the product to be 0, which is the answer. All right, I hope you have a whole lot of fun working on your assignment over this. Can't wait to see how all of you do, and I look forward to seeing you soon. Have a great day. Bye.